So this lesson is all about the central limit theorem that we're kind of within this activity discovering the properties of. So first, you should have something that looks like this for number one. Every probability is 1/6 for the different values of the roll. So we end up with either a uniform or rectangular would be the most specific way you can describe this distribution. You could also say symmetric, but because it's not a curve, the uniform or rectangular would be a little better description. Okay, then you found a bunch of means. That's what took a little bit of time on Friday. And then counted them up and then created a histogram with that. This is what my histogram looks like. Yours won't look necessarily exactly like that. Likely it was close to symmetric and either slightly skewed left or right from that. Okay, but it should have been pretty close to symmetric. Okay, so if we're comparing the two distributions, and the one on top, that's a distribution of just x values. Simple data values we can get are probabilities. The distribution on the bottom is a distribution of sample means. We took a bunch of samples from the possible rolls we can get. We did 4 at a time, found the mean of each of those and graphed that. Okay, so what you see is happening is we take a distribution that is not bell-shaped, and if we take a bunch of samples and we graph the means we get from those samples, we start to create this kind of bell-shaped curve. And the more samples you take and the bigger sample size you have, the better this curve is going to look. Our sample size was only 4 because we didn't want to add up, 40 dice at a time. But ideally, we'd want a bigger sample size than 4 when we do this. Okay, on the back, what I want you to fill in is the top bit here. So the picture on the right shows you an example of a population distribution. That one's skewed right. Definitely not symmetric. And then if we take sample means and show the distribution of that, we end up with that symmetric, normal looking curve. We can also compare the mean of both of those distributions and the standard deviation of both of those distributions. The means are approximately the same. Oh, thank you. Okay, so what you see in number 2 there, when you see, the mean symbol and then the subnotation x bar, that means the mean of the sample means. So this is referring to the mean of this distribution on the bottom. Okay, and it's approximately equal to the mean of the population. So that's referring to the mean of this guy we have on top. Okay, so anytime you see a little x bar subnotation, it's talking about the distribution of sample means, not the original data. Okay, then we talk about standard deviations of both of them. The standard deviation of the sample means, okay, again, the graph on the bottom right there, is equal to the standard deviation of our population divided by the square root of n, where n is our sample size that we take. So for our dice problem, our sample size would have been 4, because we did 4 samples, 4 rolls at a time. Okay, so now let's get this loaded up here. Okay, so let's test out this theorem and kind of see where these numbers are coming from. In this first table, we're going to calculate the mean of the population, and we're going to compare it to the mean of your sample means. All right, so the first 2 columns are just what you had in number 1 on the other side. The values of the rolls, 1, 2, 3, 4, 5, 6, and the theoretical probability of rolling each of them was a 1/6. Review from the last chapter, 2 chapters ago. If I want the mean of a probability distribution, I just take each of the x values, multiply by their respective probabilities, and then add them up. So that's what we're going to be doing in the third column, all of our x's times our probabilities. I'm just going to keep them as fractions. 1/6, 2/6, 3/6, 4/6, 5/6, and 6/6. If I take all of those guys and add them up, we get 21/6, which equals 3.5. 7 halves or 3.5. Okay. Now, let's compare that to hopefully the mean that you calculated on Friday. When I did it, I got a mean of like 3.42 something. What did you guys get? Anybody want to give me a couple of their numbers? 3.43. 3.43? Give me some more. What else did we get? 3.86, 3.7. 3.7, 3.6. Do you guys see how we're all hovering around that 3.5 number? Okay, so what you should be able to recognize from this is that the mean of the population, which is our theoretical roles, is equal to, or approximately equal to, in theory it's equal to, the mean of our sample means, which is the 40 roles that you had and finding the mean of those. Okay, then on the bottom, we're going to calculate the standard deviation, the theoretical standard deviation of rolling our die, what that would look like. Okay, so the first two columns again, just 1, 2, 3, 4, 5, 6. Theoretical probabilities are 1, 6. I left a little row at the end on this one for a summation if we need it. Okay. And we are going to use the fact that we know the mean from above. The mean is 3.5. Okay. The formula, this formula is for variance. Remember, if we want standard deviation, we take it one step further and do the square root of that. That's the formula that we're using. So the three pieces we need to add to this table are, bless you, our deviation, x minus mu, our deviation squared, x minus mu squared, and then that deviation squared times the probability of each respective x. And then we're going to add them up. That'll give us variance. Take the square root to get the standard deviation. Okay, so each x value minus our mean. So I'm going to take each x, each value of a roll, and subtract 3.5. 1 minus 3.5, negative 2.5. 2 minus 3.5, negative 1.5. Negative 0.5. And then positives 0.5, 1.5, 2.5. Remember, if you want to check, all of your deviations should sum up to 0. Okay. Then we're going to square each of those. 6.25, 2.25, and 0.25. And then because they're symmetric here, I'm going to get the same numbers again. Okay. Then we take those deviations squared and we multiply by the respective probabilities. They're all going to get multiplied by 1/6, or just divide by 6. So for the first one, I'm going to get to 3 decimal places 1.042, 0.375, 0.042, and then because I have the same numbers again, they're going to repeat. 0.042, 0.375, 1.042. Okay, add them all up. I did not type that in right. Let's try that again. 1.04. Okay, I got the sum 2.918. Okay, and that's the variance. So that's our little sigma squared. So if I want to take it one step further and get my standard deviation, I'm just going to do the square root of that number. And I get 1.708. Okay. Or, yeah, 1.7, not 0.17. There we go. Okay, so that's the standard deviation of all of my probabilities of rolling a die, in theory. Okay, I'm going to take that number and I'm going to divide by the square root of n. 1.708 divided by the square root of n. N is how many data values, how many means, or how many values we use to get each of your mean in each sample. It was 4 for our die. We rolled 4 at a time. So I'm pretty much just going to divide that by 2, and I get 0.854. So we're saying that that should be the standard deviation, or close to the standard deviation, of all of those sample means when they're graphed. Okay, so you guys on Friday found the standard deviation of the sample means from all 40 of your values. Did you have something close to 0.85? Hovering around that maybe between like 0.7 and 0.9? Okay, and remember, we had a really small sample size. 4 is really small. Ideally, in theory, we want to have sample size of at least 30 at a time when we do this. And 40 rolls isn't a whole lot. So we should see values that are much closer when the sample sizes get bigger and we have more samples. So how do the values compare? So that's that bottom formula. The standard deviation of my sample means is approximately equal to the population standard deviation divided by the square root of n. You should have values that are close there. Okay, so we are going to use this theorem about the population standard deviation and the population mean compared to the standard deviation and the mean of the samples. It's very wordy, all of this, sorry. To answer some questions now on the other page, okay? All right, the first two slides I have here are not ones that are on your packet. It's just kind of a visual representation of what we're talking about when we're doing this. So what you see in yellow, the rectangle, that's our population. And within that population, we're taking a bunch of samples, and each sample has its own average. So sometimes the values overlap, sometimes they don't, depends on what we pick. But in this picture, we have 5 different samples and 5 different sample means. Okay, then we take our original data, which in this picture is that pink graph. Okay, so almost symmetric, but it's skewed right a little bit. And we compare it now to our distribution of all those sample means that we found. And you can see that's the one in purple there. The one in purple becomes more centralized around the mean, has the same mean as the original one, but the standard deviation is always smaller because it's the original standard deviation divided by the square root of n. So when my standard deviation becomes smaller, it pushes all the data, it centralizes it, that's where it gets its name from, towards the mean. And because that happens, it actually gets a little taller too, because remember the area under any of these curves is 1, okay? So if I want to push it closer, it's going to get taller also to accommodate for all that area we're talking about. Okay, and then because I've created a normal curve, remember that was a condition of us using that z-score chart. It's a standard normal chart. It has to be a normal curve. It has to be standardized for us to use any of our z values and calculate any of those probabilities. So this theorem is a big deal in statistics because it allows us to take any set of data, no matter what it looks like, and standardize it so we can use these scores to answer questions about the probabilities within that data. Okay, so this is the first slide you guys have on your packet. The formulas are the same at the bottom that we've already talked about. At the top are the 2 conditions. One of these 2 things must be true for you to be able to use the central limit theorem. If neither of these is true, you just say, I cannot answer the question based on the information given. Either, number 1, your sample size is greater than or equal to 30. So if we were looking back to our dice example, we didn't meet that requirement, but we just used that for a sample anyway. And then number 2, the population is normally distributed. Okay, so we want to make sure going forward now that one of both of those is true. And usually it's your sample size that we're looking at, but occasionally they'll throw in the words, this population is normally distributed, and you don't have to worry about it. Okay. All right, so let's practice a problem using these formulas. A study analyzed the sleep habits of college students. The study found that the mean sleep time was 6.8 hours with a standard deviation of 1.4 hours. Random samples of 100 sleep times are drawn from this population, and the mean of each sample is determined. Find the mean and the standard deviation of the sampling distribution of sample means. Okay, so we can see at the curve here, it doesn't say it anyway, but we can see that this is definitely not normally distributed. We don't have that nice symmetric bell shape. But we have samples, we have 100 sets of samples that they found means. So my n value is greater than or equal to 30. In this case, my n is equal to 100. So we meet that condition even though we don't have a normally distributed set of data. Okay, we also know that the population mean, that's not a mean, let's do that one first, is 6.8, and my population standard deviation is 1.4. The question is asking us to find the mean and the standard deviations of sample means. Okay, so what we're calculating is the mean of sample means and the standard deviation of sample means. Okay. The mean of sample means, according to the central limit theorem, is approximately equal to the mean of the population, which is 6.8. That is your answer. They have the same mean. The standard deviation of sample means is equal to the standard deviation of the population divided by the square root of n. The standard deviation of this population was 1.4, divided by the square root of n, divided by the square root of 100, so pretty much divided by 10, gives me 0.14. Okay, and those are the two answers to my question. It also says to sketch a graph of the sampling distribution. I'll show you what it looks like. We have a mean of 6.8. We have a standard deviation of 0.14. It looks something like this. Okay, now I think it's nice to see this picture on top of the other one, which I don't even know if I can draw that very well. The other one looks, I don't know, something like that maybe. Okay. You can see that it's condensed all the data towards that mean, 6.8, and it's made it much, much taller because my standard deviation has shrunk. Okay, so now if I look at values that are on the far ends of my data, like if I look at 2 or 3 is fairly likely within the data itself. But if I say, what's the probability that an average number of sleep hours is 3? Now, if I'm looking at that, that's pretty low. If I take 100 people's sleep time and I find the average of it, the likelihood that the average of 100 people is at 3 or the average of 100 people is 100 is pretty unlikely. The averages are going to condense towards the average of the population because we're accounting for lots of data values within each state. Okay, so that's why this is happening. Any questions on that? All right. So because we have shortened periods, we're going to kind of skip over the ones that are the same. So we're going to skip over this one. Same sort of idea. Let's jump to this problem. Okay. It says the probability in the central limit theorem. So now we're going to actually take this one step further and calculate a z-score. Z-score formula is going to be adjusted slightly and be able to answer some questions about probability now that we have this theorem. All right. So the formula what? Okay, so this is the z-score formula that we're used to. We take our x value, we subtract our mean, and we divide by the standard error or the standard deviation, okay? Now, if we're talking about a distribution of sample means, we can just take each x that I have and replace it with an x bar, a sample mean that we're going to be calculating a probability if it's less than, greater than, or between. Okay, and then it's no longer a mean of the population, it's a mean of sample means, and it's no longer a standard deviation of the population, it's a standard deviation of sample means. Everything has to do with sample means. Then I can replace with the central limit theorem. I can say, well, I know the population mean is the same as the mean of sample means. Okay, so I can replace that mean of sample means with just the mean of the population. And according to that theorem, the standard deviation of sample means is equal to the standard deviation of population divided by square root of n. So my z-score formula becomes this now. I like to write it like this. Okay. There's going to be two big clues that you are changing your standard deviation, your z-score formula. It's going to talk about sample means that you're calculating a probability for. It's also going to give you a sample size. These are things that we did not see before in any of the z-score problems we were doing. There was never a talk about a sample size, and there was never a talk about sample means. If either of those things draw your attention in the problem, it is talking about a distribution of sample means, and you need to use this version of the z-score formula. It's pretty much going to work the same, except that extra little divided by the square root of n piece that we have to worry about. Okay, so the calculations are not difficult. Let me show you how this works. It says the mean room and board expense per year at four-year colleges is $10,453. You randomly select 9 four-year colleges. What is the probability that the mean room and board is less than $10,750? Assume that the room and board expenses are normally distributed with a standard deviation of 1650. Okay, I'm going to check my two conditions first. Number one, is my sample size, my n, greater than or equal to 30? No. Okay, in this problem it's 9. Okay, the next thing I look for is, does it tell me at least that my population is already normally distributed? And it did tell me that. It said that we were normally distributed. Okay, so as long as one of those is true, we're good. It also tells me that the mean room and board expense for all four-year colleges is $10,453, and the standard deviation of the population is 1,650. We are calculating the probability that Where is it? The mean room and board, okay, so it's an X bar, expense is less than $10,750. Okay, we're going to treat that X bar kind of like an X that we've been using before. We're going to first convert it into a Z using our new formula. I know I'm going to use my new formula because it talks about a sample mean. It also talks about a sample size. Once I convert it into a Z, then I can go ahead and calculate the probability with our Z-score chart. All right, so getting my Z, it's going to look like the following. It's just going to be my X bar instead of an X now, minus my population mean, divided by my standard deviation over the square root of n. So that's the new part, divided by the square root of 9. I'm going to do the numerator first. I get 297. Denominator, I get 550. And then I divide my 2. And I get 0.54. Okay. So now I can change that X bar into a Z-score statement. I can say, calculate the probability that my Z-score is less than 0.54, which is now where we need our purple packets. It's less than, so I'm going to find that value, and I don't have to adjust it anyway here. That's just my cumulative area. All right, so 0.54 gives me 0.7054. And that's my answer. Okay, so the probability that if I take 9 random colleges and find the average of all of their room and board expenses, the probability that that value, bless you, is less than $10,750 is about 71%. Okay. All right. We're going to skip the next one. The only difference in this one is it's an area to the right. It's a greater than problem. So you just at the end do 1 minus. We practiced that already. Let's go ahead and do this one. Okay. In a recent year, there were about 4.2 million parents in the United States who received child support payments. The histogram shows the distribution of children per custodial parent. The mean number of children was 1.7 and the standard deviation was 0.8. You randomly select 35 parents who receive child support and ask how many children are in their custody are receiving child support payments. What is the probability that the mean of the sample is between 1.5 and 1.9 children? Okay, so you can see just from the distribution itself that it is not normally distributed. So I want to check my sample size. My sample size is 35 parents. It's greater than or equal to 30, so we're good. Next, I'm going to name my important variable. So n, sample size, 35. Population mean, 1.7. Population standard deviation is 0.8. We are calculating the probability that if I randomly select 35 parents, the mean of all of their answers will be that they have between 1.5 and 1.9 children. Okay, we need to convert both of those values into a Z-score. So I'm going to start with 1.5. 1.5 minus my population mean, 1.7, divided by my standard deviation, 0.8. And now because it's talking about sample means and sample sizes, I know to divide by the square root of n, or the square root of 35. I'm going to get negative 0.2 on top. On the bottom, I get 0.135. And then if I divide those, I get negative 1.48. Do the same thing for 1.9. That's the only thing that's going to change in the formula. So now it's going to be a positive 0.2 over 0.135, which is going to be a positive 1.48. Okay. So now my probability question becomes, what is the probability that I have a Z-score between negative 1.48 and positive 1.48. And then we know how to calculate these. If it's a z-score or a probability between two z-scores, we just calculate both probabilities, both areas, and we subtract the larger one minus the smaller one. So if I look up positive 1.48, I'm going to get 0.9306. If I look up negative 1.48, 0.0694, and then we subtract 0.8612. About 86% of parents sampled. If we look at the means of those samples, will be between about 86%, between 1.5 and 1.9 children. Okay. All right, questions using the new z-score formula now that we have central limit theorem. Either of those. All right, we're just going to do one more question, and then we are done. I'll do this one together. All right, so in this problem, we are comparing finding a probability for x, which is what we did in the previous sections, to finding a probability for x bar, which is what we're doing in these sections, and then explaining the difference between the two. Okay, so in this one, it says college students use credit cards to pay for school-related expenses. For this population, the amount paid is normally distributed with a mean of 1615 and a standard deviation of 550. Okay, they're telling me it's normally distributed, so I don't have to worry about how big my sample size is. In the first question, it says, what is the probability that a randomly selected college student who uses a credit card to pay for school-related expenses pays less than $1,400? Okay, so it's a randomly selected student, one student, and we're calculating the probability of their value being a certain amount, not the probability of we take a sample and the mean of that's below a certain amount. Okay, so this is just our normal z-score formula, x minus the mean divided by the standard deviation. In this case, my x is 1,400. My mean is 1615 from above. My standard deviation is 550. So that's negative 215 over 550. And I get negative 0.39. Okay? And then we are calculating the probability that x value is less than 1,400. So the probability that now my z-score is less than negative 0.39 once I've converted it. And because it's less than, I'm just finding that exact value on my chart. Negative 0.39 is 0.3483. So about a 35% chance that if I select one college student, the amount on their credit cards for school-related expenses being less than $1,400 is about 35%. Okay, now for number two, the question changes a little bit. So there's two kind of clues that your z-score is going to be calculated differently. Number one, they're giving you a sample size, an n. And number two, the probability that we're calculating is now for a mean of that sample, not just a value itself. Okay, so talking about sample means. So the z-score formula is going to be similar. It's just divided by square root of n, and technically it's an x bar that we're using. The x bar is still 1,400 though, minus 1615 over 550 divided by the square root of 25. That'll give me negative 215 over 110. And I get negative 1.95. Okay, so the original question, calculate the probability that my sample mean is less than 1,400, becomes calculate the probability that my z-score is less than negative 1.95. And then we find that on our chart. Negative 1.95 gives me a cumulative area probability of 0.0256. Okay. All right, question number 3 at the bottom says compare the probabilities in part 1 and part 2. You're going to have a question like this on the quiz tomorrow, and I do not want a comparison that says number 2 is less than number 1. Okay, that's not really giving me a whole lot of information. Okay, it just says the numbers are smaller, not the probabilities themselves. So we're talking about why is the probability smaller in number 2 than number 1. Here would be a good answer. I would say, according to the central limit theorem, in the distribution of sample means, the standard deviation is smaller and the means, sorry, my computer's freaking out on me right now. It's not letting me write. Let's see if I can type it. Maybe. See if it'll recognize my handwriting. Ah, it did. Okay, and the means are equal. Okay, so according to the central limit theorem and the distribution of sample means, the standard deviation is smaller and the means are equal. Therefore, the data is more condensed around the mean of 1615, making a value of 1400 less likely in part 2 or part B. Was it part B or part 2? Part 2. Okay, so in the second group, we're talking about sample means. Mean is the same, standard deviation smaller, condenses everything closer to 1615, making 1400 more standard deviations away, making our probability much smaller. All right, that is it for the central limit theorem, and that is it for chapter 5. That's everything we needed to talk about. All right, so we have about 10 minutes left. I'll do the cell phone lotto. The rest of the period is yours. Couple reminders. 5.3 Math XL is due tonight if you have not finished that. Tomorrow, we are doing Open Note Partner Basic Calculator quiz over everything from chapter 5. So have all of your stuff organized, ready to go. And then your 5.4 Math XL is due on Wednesday. I think this date was different in the calendar, but it's due on Wednesday. Quiz tomorrow. Okay? All right, cell phone lotto. 20 is my shoddy one. If anyone claim it? Ashley? Okay. I have all your projects and your take-home quizzes from the M&M project or M&M activity graded. I just haven't put them in Blackboard yet, so by the end of the day today, you'll see both of those show up in Blackboard. You'll get them back tomorrow.